video presentation for Lecture 5 from the Structural Geology class, and I've been through this a little bit on September 6th in that lecture, but I want to go back through. There's a few clarifications, and also I'd like to complete the lecture. So the topic is deformation and displacement gradients, and in order to cover this, we need to first talk a little bit about vectors. So when we talk about vectors, we know that there's some coordinate system that is has to be defined. So usually we say, x, y, z, a Cartesian coordinate system, but and we may also say up, and then easting and northing. We know that a vector then has length, it has a direction. We can have the components of the vector in the directions of the coordinate system axes. How do we add vectors? So let's just talk through that. Here's an example of a little car, and it may have some vector as it's traveling, let's say, up and to the right. Here's another car, and that car has a motion vector that's different. It looks like it's moving to the left. And here's a third car, and that one is moving up and to the right, and maybe at a different rate and slightly different direction than the first car. So here they are all together, and we can see that in this little traffic jam example, it's maybe a good example for how deformation works in the Earth, where you can take different pieces of rock, and they can be any size, like car size, or individual mineral size, or even pieces of continents, and as they're moving, it's their relative motion that makes a difference. So in this case, we have some convergence between the lower portion of this traffic jam and this real zone where the motion changes and everything piles up, and then the one car that's heading off away is kind of unrestricted. So let's, this is a new slide I've added, and let's just call these cars A, B, and C, and each one has a vector, the velocity vector, so that has some length, which would be in miles per hour, in a direction. And so A, B, C, let's look at them then and say, all right, well, we define this coordinate system north and east, and so A then has components, so those are the portions of the vector that are in the easting direction and the northing direction, and when you add them up, you would get the hypotenuse, or the actual vector length. So the case of A, and you can see this both in the little triangle around the vector and in the table, it's moving to the north at about 46 miles an hour, but it's also moving east at 21. So when we do a simple Pythagorean theorem application, we can compute the length of the vector as 50.6 miles per hour. So then we go to B. Remember the car that's in the area where things had turned. It's actually not moving north at all, but it's moving to the east minus 33. So that means it's actually heading west 33 miles per hour. And so its length is, when we do Pythagoras, it's still 33, but it doesn't have a negative length, it's positive length. So that's important to recognize the sign change there between the component and the length itself. And then finally, C, the car that's beyond the jam, is going quite a bit faster. So the driver's happy and gave it some gas. And so that one's going 92 miles an hour north and 42 east. So it's actually 101 miles per hour. So those are our velocity vectors for each of these particles or vehicles. So another thing we might want to do is compute the differences in velocity between these vectors. And so this lets us get a sense of if they're moving closer together or moving apart. And the way we do that is we will take, in the case of B, we can take the components of its vector and subtract from those components the A components. And so what we see is, in the northern case, that A is moving 46 to the north, and B is going 0, so 0 minus 46 is minus 46, and so that shows that convergence between the two. And the same thing with easting. A is moving to the right or east at 21 miles per hour, but B is moving to the left or west at 33 miles an hour, so they're coming together at 54 miles an hour, so sign convention tells us when it's negative that they're they're closing or getting close together. And so that area between A and B would be shortening. And then we can do the same thing with C minus B. So in this case, the northing component of C is 92 minus 0 northing for B gives us a 92 mile an hour lengthening of the distance in the north-south direction between C and B. And in the case of the easting, B is moving left, C is moving right, so they're moving apart at 75 miles an hour. So you see again the sign convention there, where when that distance is increasing, the sign is positive. So shifting gears a little bit, just some definitions. When a lot of times we talk about the motions of particles, and so we want to talk about that as a displacement vector. And so we might take the position of the particle at time 1 as this position 1, and it has the position coordinates are x1, y1, z1, and then we can move it to position 2, so the subsequent location is x2, y2, z2. So the displacement vector is then that motion between the two, and the displacement vector would have the components of dx, dy, and dz, and those are just the differences. So they would be x2 minus x1, y2 minus y1, and z2 minus z1 are the components of the displacement vector in 3 dimensions. So you could use Pythagoras then to compute the displacement vector length between these two positions. So we can then talk about how if we have a field of displacement vectors, or if we have a group of displacement vectors, we call them a field. And in this case, it's a continuous field and it's uniform, so it doesn't change at all. It's constant everywhere in our view. We can have a displacement field that's continuous, so it smoothly changes, but it's non-uniform. So as we move across the field of view or across our map, we see that the displacement vectors change their length and orientation. Another thing that can happen is that we can have a break in the displacement field, and we call that a discontinuity. So that's a sharp sort of change that occurs instantaneously, something like, let's say, across a fault. And in this case, above the red line is 2 particles that didn't move at all, whereas below it, they did move, and in this case, non-uniformly. So it's important to make sure we have this nomenclature or terminology correct, and it'll help us communicate more easily. It's also important to remember that with the earlier example of the velocity vectors, we can just take a displacement vector and divide by the time over which the displacement occurred to get the velocity vector. And so then the same descriptions can apply about their continuity and uniformity as velocity vectors or displacement vectors. So now let's turn to looking a little bit at a displacement field and looking at the change in displacement over some distance. So in this example, it's an example from Hawaii, where you see in the east drift zone, it's inflating, so there's some magma that's being intruded, and as it intrudes along the east rift zone, it's pushing the walls of the rift zone apart. And so we can see, if we look at these along this profile here, I've identified these 3 vectors, but really only care about the 2 at the end. So point 1 here and point 2, we say, well, let's say this is just a profile along that distance. And what we can see is point 1 looks a little bit longer than point 2. And the length of the vectors is the scale here, see 0 to 100 centimeters. So these look like they're sort of about half that, around 50. And there's the map scale. So let's take that profile and let's just move it over so we can look at it kind of from the side. And if we say, well, the x direction is just distance along the profile, and then the u notation means the displacement vector. So over this time, due to the inflation of the east drift zone, the point number 1 at x1 location has a displacement vector of 50 centimeters. So it moved in this case, along our x1 to x2 profile, 50 centimeters. And then out at the other end of the profile, located at x2, is where point 2 is, here. That, it turns out it's 13.6 kilometers away, and point 2 moved the displacement vector u2 40 centimeters. So they're not moving the same. It's not uniform displacement, and u1's moved further than u2. And so that means there's a little bit of convergence. Think of our car example. So if we then just go through and take our elongation equation, and we say, well, let's just look at the change in length from point 1 to point 2 as a consequence of these displacements. And so here we can remember LF minus LO over LO. So the final length minus the initial length divided by the initial length. And so the final length is just the original length plus the two displacements. And so x2 is, it's, after being displaced, point 2 is at x2 plus u2. And after being displaced, point 1 is at x1 plus u1. So that, when we subtract those two, we can get that distance between the displaced points, and that would be LF. And then the original length is just x2 minus x1. And so what I did for convenience is I just said, well, x1 is at 0, so x2 is at 13.6 kilometers or 13,600 meters. So x2 plus u2 is 13,600 plus 0.4 meters. And then if we look at the x1, it's at 0, but it moves 0.5 meters. So that would give us the final length. And then the original length is just 13,600 minus 0. So we just keep going through the math here, simplifying, and we find out that the final length is 13,599.9 meters. So it's 10 centimeters shorter than it was before the inflation. So we just go through the math, and we can see that drop out. And when we come up with the final number, we see that the E is minus 7.4 times 10 to the minus 6. So it's a small number, but it does show shortening or contraction along that line. One other way to show how this can come out of some characterization of the vectors, displacement vectors, is just, in a way more simply, is just what's the change in the displacement vector length divided by the distance over which it changes. So delta U divided by delta X. And we're just assuming that the change is only in the X direction. So U2 minus U1 over X2 minus X1, do the math, we get the same result. So there had been a question in an earlier lecture about which is better to use, the elongation or the stretch. And in this case, it shows how the elongation reduces to this displacement gradient, or the change in displacement over some distance. It's a critical characterization of deformation that we want to be aware of. So now let's follow along a little bit and look at deformation rates. And so we take the Kilauea example, so what we just talked about, and say, well, is that representative? If it's representative, which we assume it is, how long would it take to build some kind of large geologic structure? So let's go through it here. So for Kilauea, we get minus 7.4 times 10 to the minus 6 is the elongation, and it occurred over 20 years. So that was the time, between the measurements of those positions, and over those 20 years, they moved the amount U1 and U2. So we can call something a contraction rate or an elongation rate, and there we just divide the elongation by the time, go through to do the math, and you can see I do a little dimensional analysis here, kind of converting from years back to seconds, just to sort of look at what the order of magnitude is. And so what you can see is in the units of per year, we get minus 3.7 times 10 to the minus 7th as a rate, an elongation rate. And remember, elongation has no units because it's length over length. So we'll see here that the units here are just 1 over time. And it can also be then minus 1.2 times 10 to the minus 14 per second. So these are deformation rates that are measured over short time scale. But if we assume that they're steady over geologic time scales, then how long does it take to build some piece of a mountain belt like what we've studied here and is shown below? So here all we have to do is we go back to our calculated elongation, and in that case it was minus 0.276. So just think of the order of magnitude. It's already 5 to 6 orders of magnitude larger than that contraction we saw over the 20 years. But if we want to divide through by time, we want time, so we can divide E by E dot, or the extension by the extension rate, and since it's year to the minus 1, the year will pop up, and we end up with 7.5 times 10 to the 5th years. So it's kind of interesting result. It says that it takes, in this case, about 750,000 years to build this little piece of a mountain belt with this kind of shortening. And it turns out that's quite true, and it's important, kind of a fundamental result. We see that mountain belts grow actually fairly rapidly over geologic timescales, and in a million years you can produce some significant relief. So fault systems in mountain belts are quite dynamic over geologic timescales, and this is a way to prove that. So this will be an exercise we'll talk about a little bit more later, but you can practice this yourself, just measuring the shortening of this bed here in Maverick Shale in Arizona. And so remember, you have the final length, which is just the distance between the two endpoints. The original length is the length along this bed, assuming that it was planar. And then if we have that same approximate shortening rate of minus 1 times 10 to the 7th, how long would it take to make this fold? Okay, one thing you probably started thinking about is that we've been talking about the elongation and the stretch as we define them is just one-dimensional, just along the final length. But we know rocks are deforming in two directions, and so they might be shortened in one way and extended in the other. And so what we in this example with these pictures here, you can see there's a few different circles, and they all have the same initial lengths, which are just the diameters. But then when we deform this, we can see that the circles turn into ellipses, and so then there's some sort of minimum final length, which is along this axis, and some maximum final length along an axis perpendicular to that. And so we can, if we take the ratios, we can call those the minimum and maximum stretches. And we could also have minimum and maximum elongations. And they'll always be perpendicular. So you can do this in 3 dimensions, and we can go from a sphere to an ellipsoid, and so it would have 3 axes. The S1 is the maximum stretch, S3 would be the minimum stretch, and S3 is some intermediate. And we usually talk about this as a sphere or an ellipsoid, but it could also be a cube going into a prism. But the points are the same, that when we look at the deforming rocks, when we want to talk to each other about deformed rocks, we want to quantify the stretch or elongation, but we also want to identify these principal stretches, so the max, the min, and the intermediate, knowing that they're perpendicular to each other. And those are the simple descriptions of the deformation that we can then use to compare from one place to another, let's say. Why that's interesting is that you can take many, many rocks from around the world. This was this study, and what they did was just measure lots of deformed rocks and kind of compare. Let's say here in the lower left would be an undeformed rock, so something that's still, a cube. But if you go up the axis here, the vertical axis, this is a case where the maximum stretch divided by the intermediate stretch is large. So we have something that kind of is really sort of elongate in one direction, and so that's what's kind of referred to as constriction. So this is like the squeezing the Twinkie or squeezing some hot dog or something in its bun, and you just squeeze it and it gets longer. But the other two stretches are similar. And then on the other end, you can have this flattening behavior where we really look at the ratio between that intermediate stretch and the minimum stretch, and this is flattening where we're sort of squishing things in one direction and the other two stretch in kind of about the same amount. And so what the result was is that we find, and this is something that's kind of fundamental about how the Earth works, is that their flattening of stretches are more common, or flattening stretch ratios are more common. So this says that it's more likely in the world that we'll see rocks at least preserved that were flattened, and that this elongation that we see in the constriction cases is not so common. So we can look at other things maybe more realistically, which is deformed trilobites or geologic features. And so here we might have the original shape of these two fossils, and then we deform them, and up here you can say, well, what do you think is the direction that they've been squished the most? It looks like it's something in kind of a upper right to lower left direction, and the greatest stretch is perpendicular to that, so sort of upper left to lower right. And it can be larger. We can really push on these things. And one thing that we'll talk about in future lectures is that when you have a line within the object that's parallel or perpendicular to the principal stretch directions, it doesn't rotate. So this one fossil here kind of is a dead giveaway. You see that the angles between the lines aren't changing much. So this is pretty much well oriented to that the principal stretch axes. And you can see it also in this little trilobite here that got really shortened in the upper left to lower right direction, but it didn't seem to be skewed very much, as opposed to these other guys that show that shearing. So that's a giveaway to us that our maximum shortening direction would be in this direction, or from upper left to lower right, and the maximum stretching direction would be opposite to that. So kind of coming to a final application of this is sort of the cumulative deformation, and how rocks might accumulate deformation over time, and how we can superimpose these different deformations as sort of represented by these two-dimensional stretch ellipses. And so this is an example of regional deformation for southern Arizona and all these different tectonic periods. And so the way to look at this is we have geologic time going from oldest to youngest on the left, and then these different events which are also decreasing in age on the top. So you can look down, you can say, okay, well, let's look at older Precambrian. Precambrian folding showed and if rocks at that time were shortened basically in this north 23 west direction, and they extended in the north 67 east direction. And the other thing you can see is not only the sort of 50% stretch ratio and the 5% in the other direction, but there was an aerial change of 52%. So in the map view, we lost 52% of the area. So you might ask, well, where did the rest of it go? It went in the air, probably the third dimension. Since this was a shortening case, that we built more topography, or there was vertical stretching to maybe compensate for that. So then we can go through time. So the younger there was this Precambrian rifting, and so we start to pull things apart, and there's a little bit of increase in area because we're extending the crust. Then we can see Jurassic faulting as another important event with the different orientation of that principal stretch ellipse. Go into Laramide folding and thrusting. We have this interesting case here of the Laramide plutonism, where there's not a large difference, this 5% versus 10% in the amounts of stretching with respect to direction, but just all of Arizona just got pumped up 115% of the area relative to what it was at the beginning of this. And that makes sense because plutons are associated with intrusion, so we're just inflating Arizona at that time. And then we continue. So in the Paleocene, Eocene, we extend the crust in this northeast-southwest direction, and that's the deformation core complexes. The Miocene faulting continues, and also basin range with slightly different extension directions. So each one of those are the individual deformation events and their stretch ellipses. But the other thing you can do is watch as we go down to the right here. This is the accumulation of deformation. So over time, we sort of keep adding these deformations to rocks that were there. So in the case of older Precambrian rocks, it went through all these deformation events. And so Precambrian rock would have this sort of composite stretch ellipse after all that deformation. And so, younger rocks might only have, a couple of deformations superimposed and so on. So this is, to me, quite an interesting figure that really shows a lot of interesting geologic history, but also this really simple quantification of it, and in a really kind of useful graphical characterization. Just the way the illustration is designed, it really communicates a lot.